All right. Hello. Welcome to Monday. So today we're going to talk about a different file system. This might be where we stop this year on file systems. I don't know. I have to think about if I want to talk about another file system on Wednesday. But so today, last Friday, we talked about the Unix fast file system. That is sort of a nice example of some very clever file system design and an early file system design. Now we're going to sort of fast forward a couple decades into the future and talk about log structured file systems. And log structured file systems, I think, are kind of a neat idea, right? Debatable how effective they are, but something that's sort of fun to study from a systems design perspective, and something that represents kind of a cool observation about how file systems work and a file system design that responds to that. I don't have any announcements, really. How many weeks do you guys have left for assignment 3? 4? From today? Oh, OK. Good luck. Get to work. I don't know. I was hoping it was like 5 or something. But anyway, who sets these deadlines? All right, so please work on assignment 3. Again, we have sort of a little bit trimmed office hours this week as the TAs are busy grading. We're hoping to have the exams back on Friday. Hoping. Might slip to Monday, but that'll be as late as it'll be. All right, so any questions about the Berkeley fast file system? So remember, there were a couple of different types of latency that FFS was designed to counteract, right? There was this, the lateral movement, right, which is the seek time, and that's something that all file systems are really trying to avoid because that's still something that hasn't gotten fast very quickly. And today we'll look at a very radical approach to doing this, right? But back in FFS days, you still even had this rotational latency as well that these file systems were trying to plan around. What sort of neat or potentially kind of disgusting thing did FFS do to deal with some of the odd rotational limitations of early disk drives? Anyone remember? Yeah, Doug.
It would spread the file out across the disk so that if the buffer filled while you were reading, you wouldn't have to go all the way around to read the next part of the file.
Yeah, so remember these old drives could actually read, their heads could read data from the disk faster than they could stream it back to the rest of the system. And so FFS, to work around this, would stagger pieces of files on the same track to make sure that they didn't fill the buffer, meaning that the disk would have to spin all the way around again. Right? So again, like very, very detailed incorporation of features of early disks. What is a cylinder group on FFS? A cylinder group, yeah.
All the data that can be read without moving the position of the head.
Yeah, that's close, right? All the data that can be read without moving the heads very far, right? A cylinder is not one track, but it's a group of tracks that are close together, and then all the data that can be read from all the platters without leaving that group of tracks, right? So it's data that's co-located on the disk. And so how did FFS exploit this fact about disks, right? So cylinder groups represent data that is physically close on the drive, meaning that the time to seek between blocks that are in the same cylinder group is going to be much smaller potentially than the general sort of latency to seek between any two blocks on the file system. So how did FFS incorporate this into its design? Who remembers? Oh, come on, I had like a whole funny slide about this. How did FFS use cylinder groups? Nobody remembers? Every cylinder group looks like a small file system on FFS. Every cylinder group has a superblock, essentially a backup copy of the main file system superblock, which stores all of the really important data about the file system. And it has its own inode maps and its own data blocks, right? And this is actually, in some ways, quite similar to the ext4 layout that we see today, right? So it's almost like its own mini file system. It's almost like it basically created a mini file system inside each cylinder group, right? So rather than one big disk, I make a lot of small disks, and then I try to put all the stuff for a particular file onto this one small disk, right? What else would I, given this design, what else would I do, what else would FFS probably want to do to improve performance? So now I'm in this nice place where potentially all the data for a single file, the inode and the data blocks associated with the file, are located in one cylinder group, meaning that they're all pretty close together. What else would I want to do to optimize performance? Man, you guys are limp today. Ooh, what happened? Is it because it's warm out? I don't know. What would I've done a nice job now of optimizing access to single files. Kevin?
I guess you probably want the files that are accessed with each other in the same.
Yeah, so ideally I'd like to put related files in the same cylinder group, right? So any file that has a probability of being accessed that's higher with certain other files, right? What's an example of a group of files that might be all accessed together that FFS might want to put on the same cylinder group? Yeah. Yeah, like app-specific files, like anything that is used by, any file that's really only used by one particular application, right? Apps with their settings and any sort of persistent state that they store in files sort of naturally create their own little universe of related files, right? And putting these together on the same cylinder group could potentially mean that while that app is running and generating lots of little I/O requests, all those I/O requests are ending up in the same cylinder group, and the heads don't have to move very far, right? And yeah, we just talked about this rotational planning stuff. Yeah, kind of wild. Anyway, any questions about FFS before we? Yeah.
Does defragmentation do a similar job?
Yeah, so it potentially could, right? So I don't even know what defragmentation means, to be honest with you. I mean, so if you imagine that a file system has been used for a while, and data is sort of spread out all over the device, right? The process of defragmentation could refer to moving things closer together, so compacting parts of the disk. So for example, so what would that mean, right? Inside one FFS cylinder group, just to make this more precise, what could defragmentation refer to? What might I want to do periodically? This would be a good exam question. That would improve the performance of my FFS cylinder group. Yeah. Okay, well remember, so that's interesting. I could try to move all, well, what would that mean in the context of a cylinder group? Yeah, so I could move data within the cylinder group to the outer edge of the cylinder group, right? What else could I do with files that would require two cylinder groups? Yeah.
Recognize files that are usually accessed in a sequence. Then
Oh, no. You've got way too complicated, right? This is simple, right? Remember when we looked at the ext4 group allocation? What did you guys notice about that? Yeah.
I was thinking maybe if the file span to one cylinder group, try to move it so it's not one cylinder, but across the board.
Yeah, I could do that. I'm not sure if some of these systems even support that, but yeah.
The multiple allocations for the same file is not good.
Yeah, so that's one thing I could do within a cylinder group, right? I probably want to move, but also in general with the data blocks, where do I want the data blocks to be close to? Remember, I mean, this is a file system that's been used and abused, It's got some history to it. There's some files that, it's not friends with anymore that are gone. They've moved on, And so what are the data blocks going to look like? Some of them will be allocated, some won't, right? But what could I do with those that would kind of sort of constitute defragmentation? Yeah.
Move them close to the inode.
Yeah, so I could certainly take all the data blocks and just move them as close to the inodes inside each cylinder group as I could, right? So that's going to minimize the seek time between the inodes and the data blocks. What else can I do in terms of looking at multiple cylinder groups? So someone pointed out, reminded us that the outside of the disk is faster to read from the inside, faster to access. So what might I want to do across the entire group of cylinder groups? Kevin? Yeah, so I might want to take files that are allocated on cylinder groups that are not on the edge. And if there's room on those outside cylinder groups, move them to the outside cylinder groups. Right? So that could also constitute defragmentation. You remember when we saw the ext4 file system metadata, it was doing that, right? It had essentially had allocated files initially from the group of blocks that was presumably the closest to the edge, right? Where the performance was the best, right? Any questions about this stuff? It's kind of cool.
What's a superblock again?
So the superblock stores all sorts of metadata about the file system, right? It tells you where the inode maps are. It tells you, how many bytes are in the file system. Remember when we had that? Wish I had the other slides up. That FS shows super stats or whatever, and it showed you the lifetime writes of the file and all this other thing. That stuff's all stored in the superblock, right? Didn't really talk too much about superblocks, but a superblock is one piece of file system metadata that's pretty critical to. So if you corrupt your superblock, you could potentially lose the entire file system. And so most file systems have a very simple way of dealing with this. They just make multiple copies of the superblock and put them all over the disk. Meaning, well, it's not that big of a data structure. Meaning that if one of them is corrupted by like a bad sector or you overwrite it for some reason, then it knows where to find a backup copy. So pretty simple. Superblocks, again, it's not a big data structure, so replicating it a bunch of times is not a big deal. All right, any other questions about FFS? So I think, again, it's important to sort of, I wanted to bring FFS back into mind so you guys have some idea about how radical a design LFS is, right? All right, so FFS circa 1982, right? So now it's 1991, right? Some of you may have been born in 1991. Wow, okay, never mind. Some of you hopefully were. What's that?
Still -2.
Still -2, yeah. Okay, so what's different about 1991 from 1982?
My brother saves the planet.
Okay, so Doug's brother is born, right? So everything I do it for you replaces Eye of the Tiger at the top of the charts. Eye of the Tiger, debatably a much better song than everything I do. I do it for you. So it's not clear that this is a move and that the world is improving here. Silence of the Lambs replaces Gandhi. Oscar award-winning film. Kevin had his hand up, so he was probably going to say something else, something was different about computers, right? Which is exactly what we're talking about. What's different about disks? Yeah. They got a little bit faster, but what did they get more, Kevin? Yeah, okay, the form factor, yeah, but yeah, we're getting there, yeah. So higher capacity, right, and bandwidth is improving, but capacity has gone up a lot more than bandwidth, right? So this is sort of the I/O crisis. Did you have? Yeah, and what else has happened to computers during this time period that's potentially different, right? So disk bandwidth is improving, right? And that means that I can, and remember, when we talk about bandwidth here, this means the bandwidth between the CPU, the processor, and the disk, right? So I can get data to the disk faster, right? It doesn't necessarily mean the disk can write it faster. But I certainly am not having this problem anymore where I only have to write 1 out of 3 sectors to deal with the fact that this bandwidth is a problem, right? But one of the biggest differences is that computers have a lot more memory, right? 128 megabytes of memory, right? It's like, wow, and yeah, this is wouldn't you guys love your OS 161 kernel to have this much, right? And one of the things that started to happen is, we have more memory in the system. And what is some of that memory being used for? What's that?
Caching?
Caching, right? But at the same time, disk seeks, right? So let's keep in mind the thing about disks that does not improve very fast, right? So I'm getting data to the disk faster, right? The disks are getting bigger, memory is getting bigger, but disk seeks are still super slow, right? So LFS is this really sort of elegant design that observes these things and says, look, essentially seeks are now my bottleneck, right? For a little while, bandwidth was a bottleneck, just getting data to the device, but we solved that problem with better interfaces. And so now seeks are the issue, right? And if I could just fix this pesky seek problem, then I could really dramatically improve file system performance, right? And at the same time, I've got all this extra memory, right? 128 megabytes more, right? Or maybe, I don't know, 64 megabytes more memory. What could I do with that? How might this help me? Somebody said it before. I'm going to use it as a cache, right? So LFS sort of emerges from two observations. One is that as I get more memory in the system, I can build a larger buffer cache. That buffer cache can absorb a lot of what? What are buffer caches really, really useful for? Yeah. Lots of reads, right? Because remember, reads are completely safe to serve from the cache, right? Caching reads in memory and serving them from memory, creates no, or I hate being categorical about stuff like that, but at least not that I'm aware of, no consistency problems, right? I can serve stuff from the cache, and that works great, right? Yeah, we did that. We did this. So as the cache gets bigger, I should be able to avoid doing any reads, right? So what's left, right? I've solved half the problem. What else do I still need to do? Writes, okay? I can still use the cache potentially to aggregate writes in memory, right? This is one nice feature of the cache, is that if I can store up dirty buffers in memory, I can write them out to disk more efficiently, right? But I still am gonna, this is where the rubber meets the road, right? I cannot have a file system that doesn't write data to disk, right? That would not be a popular file system for people to use. So if I have to do writes, so again, now you have to sort of like try to take this mental leap past FFS and traditional file systems. So if I want to avoid seeks when writing, what's the best way to do that? Yeah.
Write on the current segment, then just record that new entry.
You get it. That's close. But what about that has to do? What about that has to do with where I'm going to write on the disk? Where should I do all my writes? In the same place, right? Yeah, it's obvious, right? So it's not quite the same place, right? But it's going to be close, right? So the LFS is this again sort of landmark file system. It's invented at Stanford by John Oosterhout and Mendel Rosenblum, who's now also a faculty member at Stanford. Right? So these two clever guys came up with this idea. And log structured file systems, as their name implies, write all updates to the file, to the file system, to a log, to an append-only log. So again, it's not the same place, but you can imagine that I start at one end of the disk and I write things sequentially. And every write to the disk goes to the end of this log, okay? Obviously, there's lots of, yeah.
How would that improve the seek time? If I'm reading from someplace else and then...
Okay, so again, writes are always going to go to the end of the append-only log. Where are reads going to come from on the disk? They could come from anywhere. But why do I not care about reads? No, I mean, reads can, in LFS, reads can be all over the place, right? And in fact, LFS does a pretty, the simplest version of LFS doesn't do a very good job necessarily of putting parts of the file close together, but it doesn't care because?
You only have to do it once per file to put in the cache.
Right. The idea is the cache is going to soak up reads, right? So you got to believe that, right? If you want to get on the LFS train, you got to believe in the cache, right? If you don't believe in the cache, you just, that's the first cup of Kool-Aid. Okay? So this sounds awesome until you think about how, right? All of these data structures that we've talked about for file systems so far a lot of times file systems have exploited the fact that they put something in a particular spot and then they know it's there. Right? So what's an example of a file system data structure that we've talked about being in a specific spot on disk? Right? And the file system using that information to find and access this data structure. Kevin? The inode maps, right? Yeah, the inode maps, the inode, the inodes themselves, the inode allocation maps, the data allocation maps. I mean, a lot of this stuff is set up by file systems like ext4 at specific places, right? So I know where it is. Now I've got this I've got this append-only log. So where could that data be? Potentially. Gina.
Anywhere from the start of the log to the end of the log?
Yeah. The first word of that answer is good. Anywhere, right? Anywhere on the disk. Doesn't. Who knows? So a normal. Let's remind ourselves what we do for a normal write on a normal file system, right? So first I have to seek to read the inode map, right, to find out where the inode is for this file. Then I need to find the inode itself. Then I need to do a third seek to now the inode is going to tell me where the data block is that contains the byte that I want to. It's possible that there's a couple of other seeks in here. Why? Yeah, Gabriel.
You have to read out the data before you write it again because you have to write a whole block.
Okay, but even before I can find the data block, why might I have to do several more reads right here? James?
It could be indirectly mapped.
Yeah, so depending on how deep it is in the file, I might have to read some, like a direct block and some indirect blocks, blah, 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 right? But the point is, I have to do at least one seek to find the inode, one seek to find the data block, and then I need to actually now update the inode after I perform the block, right? So, here's how this looks. Who knows, right? I mean, and in general, again, I mean, file systems try to put this stuff close together on disk, right? The data block would probably be over here, actually, but I just thought it was fun if stuff like zigzagged around. And so this is sort of what happens normally. And we've talked about several techniques to try to keep these distances small, right? One is to make smaller parts of the file system, like in the MIDI file systems. Another one is to defragment your file system and move this stuff closer together physically, which of course generates a lot of I/O itself. It could potentially be can really affect performance. But this is your normal write on a normal file system, right? And again, if we assume that our cache here is going to soak up the reads, then the nice thing here is we just have two writes to do, right? And where are those writes going to go? On our log structured file system. Right, the data block, right? So before LFS, right, I would still have to do these writes, right? So even a cache on a traditional file system isn't going to solve this seek problem that's related to writes, right? On LFS, there's my log. There's the current inode that's going to be in memory. The current data block is somewhere. Now this is the file as it is right now, right? This is the current inode, right? This is the current data block. In order to write a byte of the file, I have to update both, right? Where do I write these new blocks? Data block, inode, right? Simple, right? The inode, now whatever inode data structures allowed me to find the data block have to be updated. Where do those get written to? The end of the log, right? So, and now what's happened here is that because I've done these updates to the end of the log, I now have I have an inode and a data block that are dead, right? These objects are not reachable anymore. They're storing stale data. And this now represents free space conceptually, right? So you can imagine as LFS goes forward, appending things to the end of the log, what it's actually doing is invalidating older versions of these data structures that are stored at some other earlier point in the log, right? Yeah, Tom.
Shouldn't it write the inode first?
Should it write the inode first? It could. Yeah, you could do those in either order. I don't think it really matters. Yeah.
You were saying something about checkpoints before, so.
Oh yeah, I don't want to introduce checkpoints into this. It's too complicated. You know, this is just so beautiful, right? Everything goes to the same place, right? And now again, I just keep appending this log, and I've taken all the seeks out of my writes, right? And the nice thing now is that when I'm looking at a write-heavy workload, I can essentially stream writes at full bandwidth to the disk. And because I've eliminated all or most seeks using my big cache, those writes just go straight to the end of the log, right? So this is a very nice solution, right? There's some problems with this, right? You guys are probably sitting there being like, this can't work, you know, I don't believe this. Yeah, so the first thing is, in order to optimize the performance of the disk, and this is true in general whenever I write to a disk, right? Particularly when I'm doing contiguous writes. I want to lump as many writes together as possible, right? So I want to build up writes somewhere and then stream them out to disk, right? So I think at a certain point, there were versions of LFS that only wrote to the disk when the buffers were evicted, when these buffers were evicted from the buffer cache, right? I want to hold them in memory as long as I can and then stream them out all at once. Now this creates sort of the usual consistency problems that you can imagine, and we can apply some of the solutions that we've looked at before and we've talked about earlier file systems, right? This is potentially a much uglier problem, right? So how do FFS and things like ext4, again, we just talked about this, how do you translate an inode number to a disk block, right? Remember, when you're doing path name translation, you're converting these little chunks of the path to inode numbers, and then you have to use that inode number to look up the next directory and load the data structure that allows you to get to the next part of the path, right? So how did FFS/ext4, how do they translate these inode numbers to data blocks? Or sorry, to disk blocks, right? I give you an inode number, you need to tell me the block on disk that stores that inode. How did they do this? Yeah.
Was it the inode map?
Yeah, they have an inode map, right? And that inode map is stored at a fixed location on the disk or multiple locations, right? Depending on how the disk is set up. But again, these are fixed places, so the file system knows where to find this stuff, right? Why is this a problem for LFS? Yeah.
You don't know where the inode maps are.
Why not? Why can't I just put them in a fixed location on disk? That sounds easier.
Because whenever you write to the end of the current file.
Yeah, so if now, I mean, in theory, a log structure file system could put them at a fixed location and it could log just in between them. But then all the writes to these inode maps are going to generate a seek, right? And I don't want to do that. So where do the inode maps end up in a log structured file system? They're just appended to the log. And so they can move, right? And so now how do I find the inode map? Yeah. So inodes are just appended to the log, and every time I log an inode, I have to log the inode map, right, to the end of the log, and then presumably keep some sort of, in-memory data structure allowing me to find the inode map, right? So you can see that all this metadata about the file system that other file systems were able to sort of very nicely store at one place, and then they always know where to find it. LFS has this problem, which is stuff keeps changing, and it keeps having to write it to the end of the log, right? So all these data structures that are in fixed locations now end up moving around. Now, hopefully I can soak up a bunch of writes in the cache, and so I can write one inode map that has a number of different modifications to it, right? So in theory, by using the cache to buffer writes and allow the inode map to sort of accumulate changes, I can write one new inode map that has a bunch of changes in it, right? But this is still sort of an issue, right? So the amount of writes I'm doing to the end of the log is starting to increase. So what about all this other stuff? The allocation bitmaps, right? I need to know which inodes are in use, which data blocks are in use. Where do you think those go in LFS? We just log it, right? If it changes, if it's got a write, put it in the log, right? Okay, so now this sounds great, right? In theory, I guess. Maybe it sounds crazy, but at some point, I have this sort of day of reckoning, which is maybe not even a day, like a minute of reckoning, right? Which is that my log hits the end of the disk. Not good. What do I do now? Gabriel?
So when you write stuff, you go back and validate it, so you can press your log and check everything back.
Yeah, so probably there's a lot of unused space on the disk, right? So every time I've rewritten an inode allocation bitmap, every time I've rewritten the inode maps, I've invalidated some earlier copy of that data structure. Every time I rewrite a data block, right? I've invalidated some earlier copy of that data that was at an earlier point in the log. So my log probably has a lot of dead space in it, right? How do we reclaim this space? So LFS calls this cleaning. Right? I'm going to clean the log. Cleaning means I'm going to essentially go through, find all the parts of the log that aren't needed anymore, and then I'm going to take all the used stuff, because remember, I want to write to the end of a log, right? So I'm going to take all the used stuff, compact it all together, and now start appending to the end of that structure, right? So take disk, remove unused parts, compress, start log at end, and keep going, right? And again, from a conceptual point of view, you can think about LFS doing this over the entire disk. But for performance reasons, namely because you don't want your whole file system like shut down for 10 minutes, like every day or so, right? LFS actually does this in segments, right? So it divides the disk into pieces, and it cleans pieces separately, right? And then the log sort of skips across these pieces, right? So here's an example, right? I've gotten, here's a segment here. What I'm going to do is I'm going to write so the way LFS does this is it usually has a dirty segment, and then it has a segment that's completely empty, right? And it goes through, it moves all the data it needs into the new segment. I don't know why I did the red first and then the green. Anyway. Maybe the red is the data blocks and the green is something else. Anyway, so this is all important. It's like Christmas. The white stuff's unused parts of the disk, right? And now the nice thing is I have a completely clean segment, right? This one has no data in it, and this has my compact log, right? So LFS was sort of always doing this at periodic intervals to make sure that it had free space that it could expand a log into. Right, and now I've created quite a bit of free space. I have this clean segment I started with, and I have a bunch of space at the end of the segment. Right. LFS sometimes to me seems like this fantastic sort of. It's not quite a bait and switch. Right, I'm going to get like hate mail from people at Stanford. If I say that. But it's like they tempt you down sort of the garden path, and then you get in and you're like, It's not as nice in here as I thought. Because, what's that?
It's like a dress spaces.
yeah. Well, this is worse. Because cleaning is a problem, right? And some of the early work on LFS, there was a lot of argument and debate over how bad cleaning was and how often you would need to clean. Because cleaning starts to depend on stuff like how much of the log is dead, how easy is it to identify the parts of the log that you don't need anymore, the compaction ratios that you're going to achieve, right? In certain cases, right, I think I talked about this. So here are some issues with cleaning, right? How often should we run the cleaner? What's the problem with running the cleaner? Yeah. Yeah, the cleaner is really I/O intensive, right? It's reading through this entire log, doing a lot of processing, and then writing it to this new log. And this is great if you have systems where you have periods of idle time, but if you have a system that's loaded most of the time, and a lot of companies want their systems to be loaded most of the time, because if they're not, why are you paying for them, right? But this can be a problem on systems that don't have those idle cycles that you need to do the cleaning, right? What about the size of the segments, right? there's an interesting trade-off here. What's good about small segments? If I make the segments that I clean in LFS smaller, what becomes more, what's the dream segment to clean? There is such a thing as LFS's like completely ideal segment that it just, you know, it goes out and has, like when it finds this to clean, it goes out and has a party, right? The easiest segment to clean. No segment? Yeah, okay. It has to be a segment, right? But that's close. It's a segment that is completely devoid of what? Well, even better than that. Nishan. No free spaces. Well, no, that's the worst, because then I have to walk all the way through it and I get nothing, right? Yeah, let's say the segment's completely full of actual live data. Not a good segment to clean, because I just did all this work, I got no reward, right? On the other hand, there is a segment that maximizes the reward because it is completely empty, right? A segment that has no live data in it, right? So if you go back to this, if this segment up here was totally white, it was all dead, then I'm done. Boom, right? I don't even have to move anything. I just mark it as clean and move on, right? Now back to the size of the segments. If as segments get blank, it's going to be more likely that I'm going to find a segment that's completely clean. Small, right? The problem is that large segments, on the other hand, amortize the cost to perform this operation, right? So if I take larger segments, I can take, you know, all of this I/O, and I can also potentially get a bigger gain. But the small segments increase the probability I'm going to find these magical segments that are completely dead. And this does happen, right? I mean, remember, a lot of this stuff in the log is dead, right? If it wasn't, then as soon as you cross the, like, my disk is full, right? That's not very likely, right? And the other, so this was the big, sorry, Gabrielle, I haven't been ignoring you.
Wouldn't you still have to walk away from a segment that was full of dead data to know that it's dead?
Yes, but you don't have to. Yeah, I think maybe. So it's possible, and I wish I understood the implementation better. It's possible that LFS has segment data structures that store some of this information, meaning that you might be able to tell without actually having to do that. Or at least all you have to do is read, right? You don't have to write a single block, right? So all you have to do is read through the entire segment, and then you go, and you're done, right? That's a good question. Any other questions about LFS? So one of the things that generated a lot of early arguments about log-structured file systems was the simple fact that the cleaner overhead starts to become very workload dependent, right? And that has to do with things like how many, what's the pattern of writes, how many writes are appends, how many writes are rewrites of existing data blocks. Remember, an append does not create a hole in the log. Updating a byte of the file does, right? So depending on your workload, you could have logs, you could have segments that were very easy to clean or very difficult to clean, right? And so when people started to measure log-structured file systems, group A would measure them and be like, this is awesome, they're really fast. Group B would use a different benchmark and be like, this is terrible, they're really slow. And so there was a lot of disagreement about this, and this generated a lot of sort of fun flame wars between some of the participants. We'll get to those in a minute. So now here, let's go back. Remember, you had to just to get started down this path, you had to believe in the cache, right? Well, let's say the cache isn't soaking up as many reads as we thought. Now what's the problem? Yeah, Kevin.
You're going to have to spend lots of time on the disk and stuff.
Yeah, because LFS doesn't really care about locality, right? It cares about locality for writes, but with reads, it's like, whatever, I've got a cache, right? Serious. I mean, that was the thing, right? It was just like, let's forget all this crazy planning I'm doing to get things laid out very carefully, and let's just things lie where they lie and let the cache soak up the difference. And here's another sort of workload dependent issue, right? Where if I have workloads that don't have good locality and end up, or if I have small caches, then this can generate a lot of seeks, right? So a lot more seeks than files, these old-fashioned file systems that don't do this clever thing of trying to write everything in one path, right? So this generated this sort of, I don't know, neat back and forth within the file systems community, sort of some sense that someone cares about this stuff. So the original LFS paper, 1991, is written by Oesterhout and Rosenblum. Obviously, when you write a paper about something like this, you say it's awesome, right? This is really cool. So now there was this, sort of plucky graduate student who re-implemented LFS and made some questions about the performance improvements, right? So, and part of this was that FFS at the same time was also improving, right? So FFS and LFS were sort of competing. She says, okay, well, we implemented some new features in FFS, and it's better than LFS now, right? So, traditional file systems win, right? Obviously, Oesterhout's not super happy about this. Yeah, I like this. This is like kind of a flame, right? They implemented it badly. They chose a bad benchmark, and they did bad analysis, right? So yeah, that's like the ultimate trifecta, right? Now 2 years go by now, and there's a second paper, right, where they again question these LFS performance claims. Here, okay, this is a little bit of a giveaway. We say LFS offers superior performance on writes. For large files, the performance of the two file systems is comparable. When you tune FFS, you get better performance than LFS. And when you tune FFS for reading, its large file read and write performance is comparable to LFS. Right? So this is probably starting to get to the point where we're doing science, right? I mean, because a lot of this is very much dependent on workloads, right? And then, yeah. So this goes on, so this is misleading. So, people, genuine, good people implement this stuff. So maybe you guys recognize Margot. What else did she do? Yeah, the torture chamber you guys are locked in this semester. Like she's the one that constructed this thing, right? She and David. She also taught me operating systems. So, anyway, so next time unless we talk about file systems on Flash, which we might on Wednesday, we'll have a lecture about operating system structure instead. Yeah. So 161 does not implement either of these, right? But if you want to do, there is